Okay. So we coming audible?
Yes.
Okay. So today is the eighth interaction session on structural vibration. My name is Devasis Panda. I'm a research scholar and Prime Minister Research Fellow at IIT Guwahati. So for this semester, I have been allocated as PMRF TA for this course. So today, what we will do today, we will go through the multi-degree of freedom systems. Basically, we will cover the free vibration part today, where first we will learn how to develop the equation of motion, and then we will go through that undamped free vibration case, how to solve the response of a undamped free vibration case. Then we will move to the concepts of mode shapes, how to calculate the responses in modal coordinates. We will see. Then we will see how to solve damped free vibration in modal coordinates, and then we will go through that two damping models. One is Rayleigh and one is Caugh damping. We will see how this damping model this damping model works, and how this actually um, mm, formulate these models. Okay, so first what we will do today, we will go through the concepts, and simultaneously we will solve the assignments. Okay, so multi-degree of freedom systems. So till now we have talked about only single degree of freedom system, where we have solved different cases, like what will be the response for uh, damped uh, SDF system under harmonic excitation, under pulse excitation, and under different kind of excitation, even earthquake excitation also. Then we moved to the response spectrum, where also we talked about SDF system. So the definition of degree of freedom, we know, like the number of independent displacement coordinates required to identify the position of the masses with respect to their original or initial positions. Okay. Multi-degree of freedom system means, that means we have more than one degree of freedom to encounter or to deal with. So here we can see a shear building model of a structure of a building. So shear building model. So it has two story. So first story has mass m1, second story has mass m2. So obviously the mass m1 can move independently. So corresponding to mass m1, we have a degree of freedom x1, and corresponding to mass m2, we have a degree of freedom x2. And at different degree of freedom, different kind of load, external load may act on this system. So if we can idealize this system as a spring mass damper system, so for the first story we have a stiffness, story stiffness, we have a some damping. We will model this damping, we will see how to model this damping and all these things, and mass, and corresponding to this mass we have a degree of freedom, and at this degree of freedom we may have some force or we may not have some force. We will see different cases. And for this second story, again we have the story stiffness K2, the damping C2, and corresponding to this mass we have a degree of freedom X2. So this we call a two-DOF system, right? So, similarly, we can have different degree of freedom. Like we may have three or four story buildings, so accordingly the degree of freedom will increase. So most of the engineering system consists, more than one degree of freedom. So that's why we call multi-degree of freedom systems, and we will learn how to solve them, and how to generate, how to develop the equation of motion, and how to solve these structures. Basically you can see that these two masses actually are coupled with each other. That means the dynamic effect of this story actually coupled by that damping and stiffness. We will see now when we will develop that coupled equation, then we will see that okay, these terms are coupled, and we will learn how to uncouple them, and simultaneously how to solve the response for different degree of freedom systems. So first, let's see how we can develop the equation of motion for the multi-degree of freedom system. So here I have considered two degree of freedom system, whatever we have talked on this previous slide. So here we have two masses. Corresponding to two masses, we have two degrees of freedom, x1 and x2, and both at the both degree of freedom, we have two external forces, say F1 and F2. And for the first story, we have a stiffness K1, damping C1. For the second story, we have stiffness K2 and damping C2. So first we will develop the equation of motion using the free body diagram approach. So if I draw the free body diagram of the mass 1, corresponding forces will have, like for mass m1 we will have first the inertia force m1 x1 double dot, because x1 is the corresponding degree of freedom for this m1 mass. And then again we will have the stiffness force k into x1. So we considered, or we assume, the linear stiffness, and this considered as the viscous damping model C1 x1 dot. That means we have already seen that in the viscous damping model, the FD, that means damping force, is directly proportional to your velocity of that degree of freedom. So simultaneously, if we solve it, like what will be the damping force, FD will be nothing but C1 into x1 dot. Okay, so for this mass corresponding to this degree of freedom and the force F1, we will have this on the left hand side, and again what is the right hand side, the force acting on this system. Now what I said, these two systems are connected to each other, so obviously we will have some relative displacement over this point when we will separate them out. So here I have separated them out, so obviously we need to identify the force component first with respect to the relative displacement. So here you can see that corresponding to K2, that K2 will subjected to that relative displacement x1 and x2 due to the force F2 and that force F1. So here this the orientation of the that stiffness force will be K2 x2 x1 minus x2. And similarly we will have the damping force over here, so C2 again x1 dot minus x2 dot. On the other hand, if we want to analyze this mass m2, so what we will have, first we will get the inertia force m2 x2 double dot, and then again due to the relative displacement k2, here at that direction we have changed the direction here, like at the direction the stiffness force will be K2 into x2 minus x1, and the damping force will be C2 x2 dot minus x1 dot. Now when you add them up, you will have, then you will see that the damping and stiffness term that due to arise due to the relative displacement of these two masses will cancel out, and we will left out at that node with this force F1, right? So the free body diagram is completed. Now we can arrange the equation. So for first degree of freedom system, if we want that want to take the summation of the all forces acting on this body, so for first degree of freedom we have m1 x1 double dot. Directions, you must take care of the directions of the forces. So m1 x1 double dot plus k1 x1 plus c1 x1 dot, plus again on the other hand we have c2 x1 dot minus x2 dot, plus we have k2 x1 minus x2 is equals to f1t, because the direction of the external force f1 is on the opposite side of the forces acting on this system. So for the first degree of freedom system we have a equation. Now again we have the second degree of freedom system over here. So for this system also we need to arrange the equation, arrange the forces in equation term. So what we will have, we have that inertia force m2 x2 plus due to this damping force c2 x2 dot minus x1 dot, plus due to this spring force k2 x2 minus x1 is equals to f2t. So we have two second order non-homogeneous equations. Now whatever I said that these two systems are coupled through stiffness and damping, we will see that when we combine them two and get the coupled equation. So if we combine these two equations in a matrix form, what we have m1, like in this if you look at this equation, so we have m1 and m2 corresponding to these two degrees of freedom x1 and x2. So if we separate out this two term x1 double dot, that means the acceleration corresponding to the first degree of freedom and acceleration due to the second degree of freedom, then we have a mass matrix, right? So we have m1 over here 0 0 and m2 over here, right? So precisely that has done here. So m1 m2, these are the acceleration of the 2 degrees of freedom. Plus, if you again rearrange the c term here, we can see that the velocity of 2 degrees x1 and x2 dot are also can be separated out from this matrix. So we have the damping matrix over here. If you rearrange the term, you will have c1 plus c2 minus c2 minus c2 and c2. And for the stiffness term also, k1 plus k2 minus k2 minus k2 and k2 over this, and this is the force. So if we arrange this in a matrix term, we will have m x double dot m matrix, this called the mass matrix, and this c into x dot is called the damping matrix, and this is your stiffness matrix. So here you can see that your stiffness matrix C and K, they contain the off diagonal terms, right? Look, these are not zero actually. These two matrices contain the off diagonal terms. That means they are coupled in a way. That means when we want to obtain the responses, we will have the coupled effect from the damping and stiffness. So we will see how to uncouple them. We have different kind of tools, like we can generally do the eigen operation, and precisely we will do during this course. So now we can see that how to develop a equation of motion for a multi-degree of freedom system. Now if we have another degree of freedom over here, say corresponding to m3, and again here some forces is acting over here, say f3, and the corresponding degree of freedom is x3. Now again, so what will happen, the size of the matrix, the element of the matrix will increase. Say for here we will have x1 double dot, x2 double dot, x3 double dot, and we will have like m1 m2 m3, and mass matrix are always diagonal matrix, they are not actually coupled. Okay. So likewise, we can develop different equation of motion for different multi-degree of freedom system. Like if we have degree of freedom system, the equation will look like this. I have added that slide. Here we have a three-dot system. So first, what you need to do, you need to draw the free body diagram of this system corresponding to 3 degree of freedom. So here we can see that this spring mass system has 3 degree of freedom, u1 for first degree corresponding to the first DOF, u2 corresponding to the second DOF, and u3 corresponding to the third DOF. So if you draw the free body diagram, you will see, and if you separate out this force, like we have damping force, we have stiffness force, we have inertia force. Again, due to the relative displacement in these two things, if you rearrange these things, so for the first degree of freedom system, we will have this equation m1 u1 double dot plus c1 plus c2 u1 dot plus k1 plus k2 u1 minus c2 u2 k2 u2 is equals to P1T, the external load acting on the first degree of freedom, right? For the second degree of freedom, that means corresponding to mass M2, if you rearrange the equation from the free body diagram, we will have this equation M2 U2 double dot plus C2 plus C3 U2 dot plus K2 K3 U2 minus C3 U2 dot C2 U1 dot K2 U1 and K3 U3, and equals to P3. And simultaneously for the third degree of freedom, we will have this equation M3 U3 double dot plus C3 U3 dot minus C3 U2 dot plus K3 U3, and K component corresponding to the third degree of freedom minus K3 and U2 is equals to 0. Now if we combine this equation number 1, equation number 2, and equation number 3 in a matrix form, we will again have some mass matrix into X double dot plus the damping matrix and the velocity vector corresponding to each degree of freedom plus k into sorry is equals to some force matrix, and the matrix will look like this. This is the diagonal matrix. The mass matrix is always the diagonal matrix. And look here, the stiffness and damping. The stiffness and damping matrix are coupled through each other, right? They are not of the off diagonal terms are not zero here. So finally, we learn how to we can develop the equation of motion for a multi-degree of freedom system. So this is like a free body diagram approach. You can also solve using the Lagrange equations. Lagrange equations already you have discussed on the last interaction session how to use the Lagrange equation to formulate the multi-degree of to formulate the equation of motion for any kind of system, like for single day of multi-dot system and all these things. So first what we need to do, we need to formulate the Lagrangian, and then we need to find out the kinetic and potential energy, and then subsequently when we apply the Lagrange equation we can find it out. So I will not go deep into it. If you go through the lecture video of the instructor, he elaborately explained these things. So let's quickly like go through the steps so that you can relate easily. Like here I have considered 2 degree of freedom system. So free 2 degree of freedom, free vibration case. That means no external forces acting on their on the system. So first what we need to do, as per the Lagrange equation, first we need to formulate the Lagrangian function, and the Lagrangian function is nothing but it's T minus V. It's a function of the kinetic energy and the potential energy, right? So for that we first we need to find out how many generalized coordinates are there, like UK. So generalized coordinates already you have discussed on the last class, is nothing but the degree of freedom. So here we have x1 and x2 generalized coordinates. Now we need to find out what is the value of the kinetic energy. T is nothing but half m1 for the first mass into x1 dot square, velocity square, corresponding to the first degree of freedom, plus m2 x2 dot square. And the corresponding potential energy will be half k1 x1 square plus half k2, the relative displacement between these two. The relative displacement is x2 minus x1 between these two systems. So x2 minus x1 square. So now we can easily formulate the Lagrangian function L, that looks like this. Now recall what was the Lagrange equation. D dt of del L, d dt of del L by del qk dot minus d dt minus del L by del qk is equals to 0. So now we need to use this equation. So first what we need to do, we need to have the first differential with respect to q dot and qk dot and qk. So here are the differentiations of that del L with respect to x1 dot and x1. So we have this, and again if we differentiate it with respect to ddt, we have m1 x1 dot. Now we have the value of del alpha with respect to x1. So here what we need to do, if we go back and again we look into that Lagrange equation, the Lagrange equation ddt of del L over the generalized coordinate, the first derivative of the generalized coordinate. So we have the generalized coordinate x1 and x2. So qk dot will be nothing but your x1 dot and x2 dot, right? So the differentiations are very easy. So we'll have these two. Now put all these values in this equation. Dt of del alpha by del x1 and del L by del x1 is equals to 0, and here all these equations are over here. If you rearrange the equation, you will get m1 x1 double dot plus k1 x1 minus k2 x2 minus x1 is equals to 0, the first equation. Now recall when we solved using the free body diagram approach, if you equate it to 0 external force, same equation we have found out from the Lagrange equation too. Now here we have done it for the first degree of freedom system. That means all the differentiations are done with respect to x1 and x1 dot. So again if you do the same exercise, del L over del x2 and del L over del x2 d dt of x2 dot, And again, if you apply the Lagrange equation in that format, like ddt of del L over del x2 dot minus del L over del x2 is equals to 0, you will find this equation, right? Equation number 2, same equation. The two second order homogeneous equations. Now, if you arrange in matrix form, you will get the same equation like mass matrix into the generalized accelerations vector plus the damping matrix into the velocity, generalized velocity at each degree of freedom, plus the stiffness matrix and the generalized coordinates is equals to 0. So that means we can use the Lagrange equation to solve to develop the equation of motion for a multi-degree of freedom system. So we have two approach. Already we discussed about these two approaches, and we already have seen like two approaches will lead to the same conclusion, right? We can use these two approaches to formulate the degree of freedom system. Okay, so these are the procedure to first formulate the degree of freedom for a multi-degree of freedom systems. Now we will see how to solve a undamped free vibration case for a multi-degree of freedom system. So for now, if you have any kind of questions, you can ask me. Then we will move to the this topic. So do you have any question? Okay. So let's see how we can solve the undamped free vibration case for this multi-degree of freedom system. So for this exercise, I have considered a 2 degree of freedom spring mass system. Undamped, that means your damping is 0. That means no damping is present in the system. Now, again, if we draw the free body diagram, we will see only you will have the spring force for this degree of freedom. It's nothing but k1 into u1. U1 is the first degree of freedom. Like if I want to generalize, if I want to define the generalized coordinates over here, so it's nothing but u1 and u2. We have 2 degree of freedom system. No damping is present there and no external force is applied on the system. That means the vibration is created by applying some or by giving some initial condition to the system. That means either giving some initial displacement or initial velocity to the system and leave it to vibrate. That means the motion is created using the initial conditions, right? So if we now uh, uh, write the equation for this 2 degree of freedom, what we will have m1 u1 double dot plus q1 plus k2 u1 minus u2 k2 is equals to 0 for this first degree of freedom system. Like here we have m1 u1 double dot at this direction plus k1 u1 minus k2 u2 minus u1 is equals to 0. If you rearrange this equation, you will get in this term. And for this second degree of freedom system, we will have m2 u2 double dot plus k2 u2 minus k2 u1 is equals to 0, because if you open this bracket, you will have k2 u2 and k2 u1. Now if we rearrange them in a matrix form, what we will have? We will have like mass matrix into u double dot plus the vector of the acceleration corresponding to each node plus the stiffness matrix k into u. And here the k matrix is actually coupled. If you form the k matrix, already we have formed it, k2 minus k2 minus k2 k2, like this. So we will see in this coupled form how we can uncouple them and how to solve for the responses. So we have this equation. Now to solve it, like recall for the SDF system also, first we have considered the general solution xt or ut is equals to some amplitude, then some harmonics sine omega nt or cos omega nt or e to the power I, that means omega t. So for this also we considered that the general solution will be in the form of that ut is equals to u the amplitude e to the power I omega t. That means like this, ut is equals to, instead of u e to the power I omega t. Omega, it's the is the frequency of this harmonics, and this u is nothing but the amplitude of this response. Now we can easily do the first and double differentiation of the ut. So u double dot t will be nothing but minus u omega square minus e to the power I omega t. Now if we substitute the values ut and u double dot t in this equation, we will have the final equation like this: minus m u omega square plus k u bracket e to the power I omega t is equals to 0, right? Now so we have this equation like this: minus the mass matrix u, that means the degree of freedom, and omega square plus k u e to the power I omega t is equals to 0. Now obviously e to the power I omega n t, this cannot be 0, because it's also one of the solution of the equation. So what we left with? We left with this term minus m omega square plus k. If we take back the common of u is equals to 0. Now this part cannot be 0. That means the inverse of this part is not existed. That means the term minus m omega square plus k inverse will not exist. If exist, what will happen?
What it is?
The u will be 0, right? That means there will be no motion. So obviously what we left with? We left with this equation. That means k.
Can you recall what is the Jacobian matrix?
Yeah, are you saying something, Nadal?
Uh,
Okay. So here we will left with this equation: k minus omega square m is equals to 0. Now this equation is very important. This equation we call the characteristic equation or the frequency equation. That means ultimately, if you look into this, like this equation multiplied by u is equals to 0, and if we rearrange the term like this, k u is equals to omega square m u. That means recall the eigenvalue problem. AV is equals to lambda v, where lambda is your eigenvalues and v are the eigenvectors. So using the eigen operation, we can now easily decouple this k and find out the responses of the system. Okay. So now if we go further, what we will have? We will have like, if we find out the determinant of this part, so what we'll have, like we have the all the matrices. Like what is the k matrix? K matrix is nothing but we have already found out is k1 plus k2, and m matrix m1 and m2, that content. So if we simplify this and take the determinant, what we will have? The determinant of this part, we will have this equation number a, like m1 m2, just multiply the determinant. All of you know how to calculate the determinant of the thing. So m1 m2 omega square minus m1 k2 plus m2 k1, it's easily you can figure it out how this equation will look like. Now the point is, when we will solve this equation, we will have four roots. We have omega 4 square, right? That means omega 4, omega to the power 4. That means we have two roots: one omega 1 square, that means plus minus omega n square, and one is plus minus omega 2 square. After finding out the root, when we will get the root of this equation, what we can do? We can easily find out what will be the corresponding mode shapes. That means we already we have correlate this equation with the eigen value problem. Now once we can find out the eigen values, these are the nothing but the frequencies corresponding to this equation, then we can find out the corresponding mode shape, that means the eigenvectors of this problem. So one we have found out the root of this equation, say omega 1, omega 2. What will we do? Corresponding to these two roots, we can solve for the mode shapes, right? Corresponding to omega 1, we have one mode shape, say for phi 1. That means corresponding to lambda 1, as we have some uh, eigenvector v1. Likewise, for corresponding to each frequency omega 1, we have a mode say phi 1. That means phi 1 will contain, here we consider 2 degree of freedom system. So phi 1 consists uh, two elements within that vector. That means these are represented at phi n is equals to phi 1n, that means corresponding to first degree of freedom, and phi 2n corresponding to the second degree of freedom. Likewise, for the second frequency, with corresponding to the second frequency, we will have again uh, two element within the second mode shape. So we will go deep into that mode shape concept little later. We will see how we can correlate the mode shape and how to deal with the mode shapes, and what that mode shape actually means. So first, let's quickly solve one example. Like, so till now what we have done, like we have solved that equation of motion, and we have uh, two eigen frequency the two frequencies. That means we converted it into that total equation into a eigenvalue problem, and find out the eigenvalues and eigenvectors. So what is the eigenvalue problem in linear algebra? Eigenvalue problem is like, what are the eigenvalues and eigenvectors? Like, eigenvectors v in a linear algebra are the non-zero vectors. If we apply the linear transformation over it, say for example I am applying linear transformation a over it, so it will either stretch or shrink by a scaling factor lambda. This scaling factor is called the eigenvalue, and these vectors, non-zero vectors of the operation, are called eigenvectors. So ultimately we frame this characteristic equation into eigenvalue problem. We frame this characteristic equation into eigenvalue problem and solve for omega 1 and omega 2. That means two natural frequencies corresponding to two modes and corresponding eigenvalues, which will tell us about the modal information, which we call the mode shape. Now we will define whom we call mode shape and all these things. So first, let's solve one example, and then we will move to the concept of mode shape and modal coordinates, and how to get the responses using these modal coordinates. So here, let's quickly solve this problem. Here, actually calculate the mode shapes and natural frequencies of this 2 degree of freedom system, where m1 the mass is given, m2 that means the mass corresponding to first degree of freedom, mass corresponding to second degree of freedom, both are given, and the stiffnesses are given. So for 2 degree of freedom system, we know the how the mass matrix will look. Mass matrix is nothing but is equals to m1 and m2. It's a diagonal matrix, so we can easily form the mass matrix. And how the k matrix will look, we have already formulated that the equation of motion for this 2 degree of freedom system. So for this system also, k1 plus k2 minus k2 minus k2 and k2. So first, what we need to do, we need to formulate the mass matrix and stiffness matrix. So as per the data, our mass matrix look like this and the stiffness matrix look like this. Then what we need to do, we need to uh, solve the characteristic equation. How? We need to first find out the determinant of the characteristic equation, and we need to equate to 0, because uh, using the concept of singularity we have solved this problem. And likewise we will do over here. So what was the characteristic equation? K matrix minus omega square into m matrix is equals to 0. So determinant of this will be equals to 0. To counter to incorporate the singularity and to find out the solution of this solution of this equation. So now you have the matrices. K matrix 27 3 minus 3 3 already we have calculated for this 2 degree of freedom system. For the 2 degree of freedom system, the stiffness matrix is calculated like this, k1 plus k2. Already you have developed this equation of motion. Go to the previous slide, you can see them. and minus omega square m. So M matrix is 9 and 1. It contains two element, diagonal element. So 9 omega square and omega square. Now what we need to do? Just simplify it. 27 minus 9 omega square minus 3 minus 3, 3 minus omega square. Now multiply, now calculate for the determinant. So you need to multiply them cross term, and minus you need to multiply these two. So uh, precisely this have done here, and finally we have this equation, right? So we have omega 1 square. If we solve this equation, we have omega 1 square is equals to 2, omega 2 square is equals to 4. So that means the lambdas, that means we have converted this into the eigen operation or eigen value problem to uncouple them. So here lambda term we have already found out, corresponding to 2 degrees of freedom. 1 omega 1 square is 2 and 1 omega 2 square is equals to 4. Now what we need to do? So we have this eigenvalues, that means the frequencies corresponding to each degree of freedom. Now we need to find out the eigenvectors. That means what we need to do? We need to again go for that k1 minus omega square m. First we need to go for the first frequency, right? Omega 1. That means first we need to use that omega 1 square is equals to, and multiplied by your that vectors is equals to 0. So first, corresponding to this frequency, we need to find out the first mode shape vector, and this mode shape vector will contain two part. Like the mode shape vector, actually the structure is like this: phi n, n define the degree of freedom, that n define the number, that means corresponding to which degree of freedom, like you can say degree of freedom. So phi 1n, phi 2n, if you have 2 degrees of freedom. And if you want to like indexing this also, so it will look like phi I n, I corresponding to your number of degrees of freedom you want to counter it. So when we will see the modal matrix, we again come back to this concept of the indexing of the modal matrices. So for now, like, let's solve this equation. So first what we need to solve it, we need to solve for phi 1. So here precisely for omega 1 square is equals to 2, write the equation k minus omega 1 square into m multiplied by phi 1 is equals to 0. So what I said, that phi 1, here we have considered 2 degree of freedom systems. So we have here and here. So corresponding to phi 1, we will have two component, one phi 1 1 and phi 2 1. So now we have the mass matrix. 27 minus 3 minus 3 3, we have already calculated it, minus what is the omega 1 square, 2 minus 2 multiplied by the mass matrix into phi 1 1 phi 2 1 is equals to 0. Now just solve this matrix. We will have these two equation, 9 phi 1 1 minus 3 phi 2 1 is equals to 0, and 3 phi 1 1 minus phi 2 1 is equals to 0. Now once we solve these two equation, we will get the value of phi 1 1 and phi 2 1. So let's solve it. So for this, what we need to do, the mode shape will look like this. We normalize generally the top, the last degree of freedom. So we take the ordinate of the last degree of freedom, say here phi 2 1 is equals to 1. Okay, because here look, we have four unknowns, we don't have any known value, right? We have two unknowns, we don't have any known value. So how to solve this equation? So first what we generally do, we normalize this coordinate to 1, the last degree of freedom, and simultaneously solve for the other ordinates. So if I take phi 2 1 is equals to 1, and using this equation I am finding out that phi 1 1 is 1 by 3. So first mode shape vector, or first mode shape comes as 1 by 3 and 1. That means what I said, that phi n is nothing but your phi 1n, that means your 1 1 and phi 2 1, the two component. That means the component over here is 1 by 3, the component over here is 1. So this is the first mode shape corresponding to that frequency 2. Now for the second case also, for the frequency 4, that means omega 2 square is equals to 4, that means corresponding to the lambda 2, that means corresponding to second eigenvalue, we need to solve for the second eigenvectors. That means corresponding to this natural frequency, we need to solve for the second mode shape. Again, formulate this equation like this: k1 or k minus omega 2 square m phi 2 equals to 0. So we will have these two set of equation: minus 9 phi 12 minus phi 22 is equals to 0, and minus 3 phi 12 minus phi 22 is equals to 0. Again, so what will happen for this 2 2, that means phi 2 will contain phi 21 and phi 22, right? So we will fix phi 22 as 1 because this is the last ordinate of this mode. So phi 22 is equals to 1, and if you apply phi 22 is equals to 1 in this equation, you will find out what will be the value of phi 21. So phi 21 comes as 1 by 3. So my second mode shape is also ready. So the first mode shape, I found out that first mode shape phi 1 is that content like phi 11 and phi 21. Phi 2, it contains two term again, phi 21, phi 22. So phi 21 and phi 22, we can see minus 1 by 3 and 1. So the first mode shape, if I draw, this is my 2-DOF system. So the first mode shape corresponding to omega 1 square is equals to 2 look like this, 1 by 3 and 1. And corresponding to second modes, that means omega 2 square is equals to 4. The first ordinate, look, it's minus 1 by 3. That means it goes on the opposite side and then come back to 1. So this is the second mode shape corresponding to this. So this system has like two natural frequencies corresponding to two modes, and corresponding to that two frequencies, we have two mode shapes. Now what we call the mode shape, why these mode shapes are important, and how to calculate the total response of a multi-degree of freedom system using the mode shape, we will see. So mode shape, first I will tell you and the definition of the mode shape and all these things. So till now, do you have any kind of questions how to solve this kind of problems? Do you have any kind of questions how to solve it? And here, look, the structure of the mode shape vectors, here I have written it. Phi n is equals to, you can notate it like that, phi jn. That means if you are considering first degree of freedom system, so 1 2, the j will become, so 1 1 2 1. Again phi 2 phi 2 phi 1 2 phi 2 2, like this. The element of this matrix will go like this. Okay, so what is the mode shape? The first question. So mode shape actually is a deflection pattern associated to a particular natural frequency. Obviously you have seen the deflection pattern of this 2-DOF system will look like this, corresponding to omega 1 square is equals to 2. The deflection pattern of this system, similar system, corresponding to omega 2 square is equals to 4 will look like this. So mode shape, what we can call the mode shape? Mode shape are nothing but the deflection pattern associated with a particular natural frequency, and it represents the relative displacements of all parts, right? Look at these shapes. It actually represents the relative displacement of this structure due to this frequency. Okay, so they are not the physical response. Okay, if we want to calculate the physical response, we need to we need to combine all the modes, then we will get the physical response. Mode shape are, we can call, they are the screenshots of the displacements. Okay, mode shape are the not physical responses, they are the time frozen screenshots of the deflection pattern, we can say. Time frozen screenshot of the deflection pattern. That means at the time instant the deflection pattern will look like this. That means if we can sum up all this deflection pattern over the time, we can have the physical response. That means the physical response will be nothing but the generalized coordinates multiplied by the mode shape. That's all. So mode shape are basically the inherent property. It doesn't depend on the force load of the structure. It will only depend on that natural frequency corresponding to each node. And mode shape will change when the physical property mass, damping, and stiffness will change. That means ultimately your frequency will change and mode shape will ultimately change, right? So now you have the concept, like, okay, what we call the mode shape and all these things, right? Now we will see how we can use the concept of these mode shapes to find out the responses of a multi-DOF system. So before that, let's quickly solve some more examples and then we will move to solve that, right? So till now, do we have any kind of questions? Okay, so let's solve this example. We have a two-story building having the floor masses. Okay, again we have a two-story building, M1, M2. So M1 is given as 2200 kg, M2 is given as 1600 kg, K1 is given as 2100 kilonewton per meter, and K2 is given as 1700 kilonewton per meter. Calculate the modal frequencies of two nodes. That means you need to calculate the omega 1 and omega 2. So first what you need to do, first you need to formulate the characteristic equation. That means K minus omega square M is equals to 0. Then you need to find out the determinant of it. You will have some equation, and solving this equation you will find out the value of omega 1 and omega 2, like what we have did here on the first example. You will get this kind of equation. Then you will have two roots, omega 1 and omega 2, and if you solve, you will get omega 1 square, omega 2 square, and under root of that omega 1 square and omega 2 square will give you the value of the two frequencies. So first let's quickly solve it. So first we need to formulate the mass matrix. So mass matrix will look like this. It's diagonal matrix by so 0 0 1 6 0 0. What will be the stiffness matrix? K for two DOF system contain K1 plus K2 minus K2 minus K2 K2 is equals to, we can find out. And here no damping term is there. So because we are solving that undamped free vibration case, so what we need to do, we need to perform this analysis, like the determinant of this K matrix minus omega square M matrix is equals to 0, and find out this equation. So just perform this equation, and after performing or solving the equation, we have the roots omega 1 square is equals to, I have found out these roots. Please go through the example and cross check it again. Okay, the steps, like you need to just do some calculations and you will find one equation like this. Here I have solved step by step, but for this example you can solve it easily like this. After getting the determinant, you will have this kind of equation, and after solving this equation you will have omega 1 square and omega 2 square. So the values of omega 1 square and omega 2 square, what I have calculated, comes as 859.5, and omega 2 square comes as this. So what will be the omega value under root of this 2? That means omega 1 comes as almost 29.32 rad per second, and omega 2 comes as 68.70 rad per second. Now in that question, if asks, okay, find out the first mode shape. That means phi 1 vector. First mode say phi 1 vector which will contain phi 1 1 and phi 2 1. How you can do it? So after you now you have the omega 1 square value 559.53. What do you need to do now? So to get it, you again need to use this characteristic equation. This, and instead of omega you need to use omega n square and phi 1 equals to 0. Now you can solve it like k, you have the value of the k matrix minus omega 1 square, you have the value, you have the mass matrix, you have phi 1 1, you have phi 2 1 is equals to 0. Now if you solve it, you will again get two equations, and you need to normalize that phi 2 1 to 1, and you can find out phi 1 1, the value of this, and you can simultaneously you can plot the mode shape, right? Now similar kind of question again, like calculate the first mode shape, that means corresponding to the first natural frequency, and after solving it the first mode shape comes as 1 and uh, 1.64. So it will be kind of phi 1 1 and phi 2 1. Here they have considered like first mode shape, so it will be the opposite of this, like it will look like this. This just change this ordinate phi to 1. Okay, so by this way we can calculate the mode shape and corresponding natural frequencies. This problem you can also solve this. So I have solved this problem and find out the values of modal information like this. Okay, so till now we have that idea like how we can decouple this coupled equation of multi-DOF system, where we have seen that mass and stiffness, these equations are coupled to mass and stiffness, and we have solved this characteristic equation, find out the roots, also find out the corresponding eigen vectors which actually represents the mode shape corresponding to each natural frequency, and we already have seen that mode shapes are nothing but the time frozen screenshot of the displacement, or we can say it's the deflection pattern associated with a particular natural frequency. It's nothing but the deflection pattern associated with a particular natural frequency. So to get the physical response, we need to multiply the mode shape with the generalized coordinates. Then we will get the physical system also. So how we can do that, we will see. So let's consider again the same system, same two DOP system. Okay, here first degree of freedom have mass m1 m2. So if I construct the mass matrix, m will look like this: m1 0 0 m2 k. The coupled in the coupled equation, the k will look like this: k1 plus k2. We have already formulated the equation of motion or generated the equation of motion. So k1 plus k2 minus k2 minus k2 and k2 is equals to 0. That means k matrix. So we will do the equation of motion. So the equation of motion will look like m, that means the mass matrix. Here already we have formulated the mass matrix into u double dot plus k. This is the coupled stiffness matrix into u is equals to 0. So it's nothing but the nth order homogeneous differential equation if we have the n degree of freedom system. So it's a free vibration case. So obviously we will have some initial condition with which we are actually generating the motion. Now already you have seen that phi n that represent the mode shape corresponding to some corresponding to a certain natural frequency or corresponding to a particular natural frequency. So the physical response and phi n, this mode shapes already what I said, these mode shapes are not the physical responses, they are the time frozen screenshots or the deflection pattern associated with such particular natural frequency. So how we can get the physical response? Physical response will be nothing but the generalized coordinate multiplied by the mode shape. So if I want to find out the response of the n degree of freedom, the physical response will look like this: phi n t into q n t. Q n t is nothing but the generalized coordinates and phi n is nothing but the mode shape. So using this modal equations, we can easily find out the physical response of a multi-DOF system. So here phi n, already I have said it doesn't depend upon time. Already I have said it's the time frozen screenshot of the displacement, and the generalized coordinates qn is the response, generalized response, modal response. We can say it depends on the time. So we have two quantities. One depends on time, and that means time variant, and one is time invariant. Now this generalized coordinate, how we can find out the values of generalized coordinates? Already we have solved the problem. Like when we have solved that undamped SDF system, we have found out the xt. The response is nothing but a cos omega nt plus b sin omega nt. Likewise, the generalized coordinate at n degree of freedom will be qnt is nothing but an cos omega nt plus bn sin omega nt. That means if I want to consider 1 degree of freedom, so q1t will be sorry, a1 cos omega 1t plus b1 sin omega 1t, right? Now, so the physical response of a system is nothing but the generalized coordinates multiplied by the mode shapes, or we can say the modal response multiplied by the mode shape. Now if we just substitute the value of qn, we will have this equation, and we can find out the u double dot t, because we need to you know uh, complete our this equation m u double dot plus k u is equals to 0. So u double dot t you can easily differentiate with respect to time. So it's nothing but it will look like this: phi n minus a n omega square cos omega nt minus b n omega n square sin omega nt. Now substitute all these values to this equation. What we will find out? So if you substitute all these values and take the common qnt, we will left with minus omega square phi n m plus k into phi n qnt is equals to 0. This equation. Now this equation look familiar, like when we have solved the characteristic equation, we have similar kind of problem. That means again in the modal coordinates, the problem leads to the eigen value problem, where we can decouple it and we can find out the responses. So now if we go further, the generalized coordinate cannot be 0, otherwise there will be no motion. So we left with this part is equals to 0. So we have k phi is equals to omega square phi n m. Again it's the matrix eigenvalue problem. Now how to solve it? Again we need to find out the determinant of this thing, because this will look like not look like the a lambda is equals to lambda v. That means eigenvalue problem in linear algebra, similar kind of thing. So again in the modal coordinates also, so this coupled equation we can uncouple using the eigenvalue problem. Now what we need to do, we need to find out the determinant of this characteristic equation, then we need to look for the roots of this equation, and we can correspondingly or simultaneously solve for the degrees of freedom. So now at the beginning I said that in one matrix, like we have n degree of freedom system, like, so for n degree of freedom system we will have n natural frequency, and we have n number of mode shape. For the 2 degree of freedom system, we have seen that we have two natural frequencies and two mode shapes. Here we have already seen two natural frequencies and two mode shapes, right? Corresponding to these two natural frequencies, we have two mode shapes, and these two mode shapes phi 1 and phi 2. So if we have n number of degree of freedom and we want to arrange all the mode shapes in one matrix, we call this the modal matrix phi, the capital Phi, the modal matrix phi. So the structure of the modal matrix is like this: phi j into n, that j indexing the DOF and n indexing the mode number, the DOF and the mode number. So if we write down the matrix will look like: the first component will be first degree of freedom, first mode. Then here, as per this column, then what will be the second degree of freedom for first mode. Again, n degree of freedom for first mode. So that means the first component of this modal matrix will be phi 1. That content phi 1 1, phi 2 1, dot 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 phi n 1. The structure like this. That means the element of this matrix will contain the mode shape corresponding to each mode. Again, if you look at this, this is nothing but your phi 2. This is nothing but your phi 3. The mode shape corresponding to third mode phi 3. This is nothing but the fourth mode phi 4. Right? So the combined matrix we call the mode shape matrix. Right? Whose each of the column contain the mode shape. Okay. Now again, for the n eigenvalues, if we rearrange them in one matrix, like we have omega 1 square value, we have omega 2 square value, we have omega 3 square value. If we have n degree of freedom system, we have omega n square value also. So if we rearrange them in a matrix, we call it spectral matrix. So the diagonal term of the spectral matrix are nothing but the corresponding eigenvalues. That means omega 1 square, omega 2 square, omega 3 square. So now using this modal and spectral matrix, we can write that complete equation k phi is equals to m phi into omega square. What is that omega r square? It's nothing but the spectral matrix. The each component is a diagonal matrix, and each component of the matrix contain the the corresponding eigen values, and the modal matrix content the mode shape information. Each column of the modal matrix is the mode shape corresponding to each natural frequencies, and the structure is like that. Each component will have phi chain. That means the first row, a first column will give us the first mode, the second column will give us the second mode, the third column, and likewise the nth column will give us the nth mode shape of the multi degree of freedom system if we have. Now so uh, till now, do you have any kind of questions? Okay then. So now the next thing is we will spend some time on that orthogonality of modes, like regarding the modes and what will be the property and other things of the modes. We will see. Then we will go to that how we can find out the physical response of a undamped system. So few properties you need to know about the mode shapes before moving forward. So the first property is the modes are orthogonal to each other. That means your that K matrix, that means modal stiffness matrix, will be diagonal. That means we have started with a coupled matrix where we have seen that off diagonal terms are not zero. Now after the modal operation, we have seen, okay, my modal matrix will be diagonal. So what will look like? That means phi transpose k phi is a diagonal matrix. And similarly, phi transpose M phi, again, it's a diagonal mass matrix. That means each component of this matrix, like the Kn, the n component of this matrix will contain phi n transpose K phi n. Likewise, for M matrix, Mn, nth component of this M matrix will be phi n transpose M phi n. We call them normalized mass matrix, normalized stiffness matrix, modal mass matrix, or modal stiffness matrix, right? Now, we can also say that M and K are the positive definite. So, we can prove that, okay, it's actually the transformation actually leads to the same equation like K is equals to omega square M, right? And also the modes are orthonormal to each other. That means I dot I will be equals to 1, but I dot j will be 0. That means phi ith mode multiplied by phi jth mode equals to 0, but phi ith mode into phi ith mode will be 1. That means when, if we want to write it down like this, phi I multiplied by phi j, if I equals to j, it will be 1, and if I not equals to j, it will be 0. It's a very important property of the mode. Also, modes are orthonormal to each other. Then same property, phi transpose n, phi n transpose phi n equals to 1. If your n is equals to, that means n is same for these two. If we like indexing like this, phi n transpose phi r is equals to 0 when n is equals to not is equals to r, and when n is equals to r, it will be 1. So this is a very important property, like modes are orthogonal to each other and also modes are orthonormal to each other. That means if we can only multiply the mode same, that means the mode corresponding to same degree of freedom, we will get some value, otherwise it will become 0. So again, the modes are normalized with respect to different things also, like we can normalize it to unity, that means which leads to the amplitude normalization and mass normalization. Say for example, if we have some vector, okay, say we have some vector u, say u1 vector. Now if I want to normalize this thing, normalize to unity, say for example I want to normalize this thing, what I need to do? The normalized vector u will be nothing but the vector, say for example this is u1 vector, so normalization u will be u1, that vector itself, divided by the Euclidean norm of u vector. And what is that Euclidean norm of the u vector? It's nothing but under root of u1 transpose dot u, that means under root of u1 square. So here is the vector, so you need to take care of the dimension, so we can write it like this, u1 transpose u. So if I want to normalize any vector to unity, we can use this. It's nothing but vector itself divided by the Euclidean norm of the vector. So we can call it the normalization, normalization to unity. So in this proof, you can also see that normalization can be done like this. Say for example, we have a vector u1. Let's say for example, this u vector contain two component, 1 by 3 and 1. Okay, now let's say what will be the value, let find out the normalized to unity value of this u. How we can find out? So you need to just perform this task, like it's nothing but the vector divided by the Euclidean norm of this vector. So here you just do this um, calculation. So u vector is nothing but 1 by 3 1 transpose divided by Euclidean norm of this, that means under root of, you just need to do the calculation, 1 by 3 1. Either you can use the calculator, or these are like 2 cross 1 and 2 cross 2 matrix maximum, so you can solve it by using hand also. So ultimately your normalized matrix will become like this, 1 by root 10 and 3 by root 10 transpose. That means when I normalize it to unity, this matrix will look like this: 1 by root 10 and 3 by root 10. Simple thing. So likewise, we can do the mass normalization and amplitude normalization of the modes. Say amplitude normalization, that means we make the amplitude of the last mode to 1. Like last mode, already we have seen that for the first mode, we have seen that phi 1 1 and phi 2 1, we consider phi 2 1 is 1. That means we normalize it. For the second mode also, we have seen like we normalize this ordinate like phi 2 2, right? So it's called the amplitude normalization. Say we normalize the amplitude of the top story, always the top story, that means the last degree of freedom of the system, we make it to unity. How? Just say take one ordinate 1 and solve for the other ordinate, you will eventually normalize it to 1 of the last. And what is the mass normalization? Mass normalization means like we have the normalized mass matrix, that means a main will be 1, that means phi n transpose m phi will be 1. Okay, and this is nothing but like mn is represents the nth component of your mass matrix m. So ultimately what we can say, mode mode shape matrix or modal matrix multiplied by modal mass multiplied by again modal matrix is equals to a identity matrix. This we call mass normalized mode shape. So mass normalized mode shape, that means the mass actually normalized with corresponding to the modes, and each of the this mass matrix will contain this value phi n transpose m phi n. N क्या है? What is that n? Corresponding to that particular degree of freedom. So if we are looking for the first element, so n will be 1. If we look for the second element, the n will be 2. Likewise, it will increase. So for example, like this problem, the mass matrix and modal vector, modal vector or mode shape vector, whatever said, that big phi, that means this is nothing but phi 1 and this is nothing but phi 2, which contain two element phi 1 1, phi 2 1 and phi 1 2, phi 2 2, right? Now calculate the modal mass. Calculate the modal mass. That means you need to normalize with respect to the mode shape matrix. So we have the mass matrix M 200 0 0 100, and we have the phi matrix. That means the mode shape matrix or the modal matrix 0.5 1 minus 1 1. So what do you need to do to find out the normalized mass matrix or modal mass matrix? Is nothing but you need to do the matrix operation phi transpose m phi. So phi transpose, you need to do the transpose of this matrix. So 0.5 minus 1 1 1 multiplied by m 200 0 0 100 multiplied by again phi. So first what you need to do, first do this two matrix operation and then again multiply with this, you will get the value as this. So my modal mass matrix or the normalized mass matrix with mode shape with respect to the mode shape will come as 150 0 0 300. Great. Okay. Now here again we have a problem like it's a tricky kind of problem. You can easily solve it like I just explain it. Determine the natural frequencies and mode of vibration of the given system so that the mode satisfy the orthogonal property, right? Orthogonal property, that means your phi transpose m phi and phi transpose k phi, you need to show it like phi transpose m phi is equals to 1. Your goal is ultimately showing that. So first we will just stick to this first term, like find out the two natural frequencies. Once you can find out the two natural frequencies, you need to find out the corresponding mode shapes and then Once you find out the mode shape, you can do the mass normalization, and you can show that okay, these modes actually satisfy the orthogonal properties, right? So just go through this example. You will see it's very similar, very easy example. Like for the first degree of freedom, we have U1. For the second degree of freedom, we have U2. And for the first degree of freedom, corresponding to the first degree of freedom, we have mass M1. For the second degree of freedom, we have mass M2. So mass matrix will be ml by 4, 0, ml by 2, because two masses, and k, the value of stiffness matrix, is already provided. Okay, you don't need to calculate it. What you now need to solve it, you need to find out the determinant of the characteristic equation, solve it, and you will find out omega 1 and omega 2 value. And once you find out the omega and omega 2 value, you can say, okay, these are the first two natural frequencies of the systems, and corresponding mode shape, we can find it out. Okay. Now we will see, till now we have the concept of mode shape, different kind of terminologies related to modes, and we have seen that we can find out the physical response by combination of the generalized coordinates and mode shape, generalized coordinates and the mode shape. Now precisely we will see, using this modal representation, how we can solve the response of a undamped free vibration case. Okay. So till now, do you have any kind of questions? You can ask me, or we will move forward. Here, precisely we will see how we can now find out the responses of a structure using this modal representation. Okay. So let's quickly explain these terms, and let's solve some.
Hello,
Yeah, Bob.
devices. How is this things applied practically?
Yeah, practically
Like
it's,
after your calculations, and how do you, use it to make a decision?
yeah. So first thing, when I solve any kind of multi-degree of freedom system, I look for that, can I write it down in the modal coordinates? Because in a multi-degree of freedom system, say for example, you have a building, right? You have a 3-story building, or 5-story building, or 7-story building, say for example. That means you have, say, end-op system. Okay. So for this end-op system, obviously you will have n frequencies. Now, if I want to solve the response of the system, if I know the deflection pattern, that means the mode shape corresponding to each of these natural frequencies, I can find out the physical response. X of t or u of t is nothing but your summation I is equals to 1 to n phi n and your qnt. So it's very helpful to find out the responses of a multi-degree of freedom system. Got it? So we generally
Okay.
use this approach everywhere. Like I am solving the turbine considering 21 degree of freedom system. So obviously I will look for the modal coordinates. In modal coordinates, I have written down the equation of motion. Say for example, this I have already explained this. Like if we have this system, two-DOF system in free vibration case, okay, so the physical response will look like this. Already we have solved for the general coordinates, and the physical response we can easily find out using this sort of equation. We will see actually how we can use to solve multi-degree of freedom system. That means the equation is quite simple. The physical response is nothing but summation of the mode shape and the generalized coordinates. That means you just need to add this. What are the mode shapes? Mode shapes are nothing but the time frozen screenshot of the deflection or the responses, mainly the deflection response. If you can add them, sum them up, you will have the response. Yes or no? And we are looking for the response. Any kind of system, what we are looking for? We are looking for the response under any kind of loads or any kind of systems, right? So here
Okay.
for
Thank
for
you.
for the end of system, if we want to write down the equation of motion for n degree of freedom and then try to solve it, it will be very time consuming and very problematic. Now just you have a simple and says sort of equation which can be easily solved. Like The problem of coupling also solved, the problem of computation also solved. You just need to solve this equation iteratively to get the response. Say for example x1t, for this degree of freedom I want to find out the response. X1t will be 1 to n phi 1 q1t. That's all. Okay. So now how we can express like the question further, if we want to explain his question, like if we have this 3 degree of freedom system, say we have mass m1, m2 and m3 corresponding to degree of freedom u1, u2 and u3, how we can solve the responses, right? So what we can do, we know the modal displacement of this system is nothing but summation of the mode shape into generalized coordinate. So summation of this total mode shapes already we have defined in a term of modal matrix. Here I have defined it in a terms of modal matrix 5 that contains all the information of the mode shape. Then each of the column represents the mode shape of corresponding to each degree of freedom. Now here, so we can write it like this, where QR are nothing but the generalized coordinates or the modal responses. We can easily find it out, like for a single DOF system I need to find out q1. What will be the q1? I know for a single SDOF system undamped case, I know that a cos omega nt plus b sin omega nt. So corresponding to omega 1 my q1 will become that. So for this degree of freedom I can easily calculate the physical response, right? So what will be the q value? It's nothing but q1, q2, q3. How much we have the degree of freedom until that. So my physical response is nothing but summation of these three. Now if we want to further simplify this equation, multiply both sides with phi and t. Like we just want to use the property that orthogonal and orthonormal property of the mode shape to simplify our equation. So if we multiply phi and t into m with both sides of this equation, our goal is to apply the orthogonal property of the modes. So that's why we are doing it. So here we can see that the equation become phi n transpose mu is equals to summation r is equals to 1 to n phi r q r phi n t m. Now uh, here you can see the orthonormal property and orthogonal property of the mode shape. We know phi n transpose phi m will be equals to 0 when n not equals to m, and when n equals to m we will have the value 1. So here within that summation, that r and r will be 1 only r equals to r. That means r equals to n. Here we have considered two here we have considered the two parts, like one is n and one is m. So all the part of this summation will be vanish, only the part where r is equals to n, that means here m is equals to n, will sustain. So we can write it down, phi n transpose mu is nothing but phi n qn. That means only the index with only the terms with same indexing, otherwise the all term will be vanished due to orthogonal and orthonormal properties. Phi n transpose m, right? Now if you again simplify this equation and look for this qn, that means the generalized coordinate qn is nothing but phi nt m u, that means that response vector divided by phi n transpose m phi. That means what is that quantity? Phi n transpose m phi n is nothing but mass normalized or normalized mass matrix m n, right? So this is actually the equation for the modal contribution factor or the modal coordinates. How we can find out the this physical or the modal response this way. Phi n transpose m u divided by m n. Either this is the normalized mass matrix or we can use phi n transpose m phi n. So now I will show you how we can use this equation and solve for a free vibration response case. So just you need to remember this equation, or this equation is very straightforward. We just start with that physical response is nothing but that mode shape into QR. Then we have mm, multiplied phi nt and m to use that orthogonal property of the mode shape, and finally lead to this quantity. Thus u is the responses. Like for this system, say for example, for 3 degree of system, I am providing you initial displacement as say 0 0.1, 0 0.2 and 0 0.3, and I'm telling you, okay, find out the modal coordinates or modal contribution or the modal responses of the structure. How you can find out? You can directly use this equation and find out the modal responses at each time point. Like if you want to solve this equation, sorry, this problem, I think this problem is with from your assignments. So like here, the displacement of the modal system is expressed as x is equals to phi into q. Already I have seen that physical response is nothing but the mode same matrix multiplied by the generalized coordinates. So that q is the modal coordinates and n phi is the modal matrix. Calculate the modal coordinate q for two-story building where the displacement x, look, u initial displacement, they have given the initial displacement 2 and 3. Mass and modal matrix are given. So what you need to do, you need to find out q1 and you need to find out q2. How? This is the formula. So phi n transpose mu, phi n transpose mu, or instead of u here you can use x, right? U or x the same, right? They define the degree of freedom, and phi n transpose m phi. For the q2, what do you need to do? So for the q1, the n will become 1. For the q2, n will become 2. That means phi 2 transpose m u vector divided by phi 2 transpose m phi 2. Now, what we need to do? We need to solve these two matrix operation. First one is this and second one is this. Great. So look, do we have the mass matrix? Yes. Do we have the modal matrix? Phi? Yes. So what we need to do? We need to find out phi 1 and phi 2. So what I already said, each of the column of the modal matrix will give you the mode shape. So this is nothing but your phi 1 and this is nothing but your phi 2, right? So write it down. Phi 1 is nothing but 0.51. Phi 2 is nothing but minus 1, 1. Now you just need to do the operation. First, just solve for the denominator. It's nothing but this m. So m is phi transpose m phi. So directly here that m, uh, for the denominator part, you can see that directly we can solve for that particular degree of freedom. So here total that phi matrix is taken it. That means like if you go for the solution, it will look like it will come as 450, 0, 0 and 900. Now what you need to do, you need to solve this equation phi n transpose m phi and this. So phi 1, what is the value of phi 1? Already I have extract it from this phi matrix, 0.51 and minus 1, 1. So transpose this means it become like this, 0.51, 600, 0, 0, 300. Again multiplied by phi. That means you need to make it phi 1 and phi 2. In between phi 1 and phi 2, right? Phi 1 and phi 2. So we have phi 2 is minus 1 and 1 and phi 1 is 0.2 and 0.2, and we have this x value or u value is contain this vector 2 and 3. So we have 2 and 3, and already we have calculated the denominator 450. So the value of q1 comes as 10 by 3. And simultaneously, if we solve for q2, so let's say I will solving for q2 here. So q2, what will be the value of q2? It's nothing but phi 2 transpose m u or x divided by, that means this, divided by your mn, normalize one. So phi 2 transpose, we have 2. This is your nothing but phi 2. The second column of the model matrix, minus 1, 1. Now the mass matrix, we have this 600, 0, 0, 300 and u. That means 2 and 3. Divided by, we have this, multiply that second element of the mass matrix, that means phi, this phi n transpose m phi, that means the second element of the mass matrix. So phi 2 transpose m phi 2, that means the second element of the mass matrix, normalized mass matrix, minus 1, 1, and do the operation, divided by you will have 900. So by this way you can find out the modal contributions, and once you have the modal contribution factors, you can easily find out. So let me quickly brief you once again. This mi is nothing but the ith component of the normalized mass matrix. That means it will contain phi I transpose m phi I. So for the first component we have 50, and for the second component we have 900. By this way we can solve these systems. Okay. Now we will come back to the equations where we can easily solve for the responses using considering all of the modes. Like, what was the physical response? Is nothing but the modes of matrix into generalized coordinates. Now if we uh, you know mm, elaborate this into the matrix form, what will this, for corresponding to u1 we have a displacement, we have velocity and acceleration also. So we are now considering the displacement physical response, the physical response displacement. Great. So what will be the physical response? So the mode shape matrix, this is nothing but your, that means I am writing that u is nothing but that phi, the big capital phi, that means the modal matrix, into q. So here we have considered 3 degree of freedom system. So we have 3 displacement, we have this mode matrix and the modal responses. Mode matrix into modal responses. Now if we want to convert it into the algebraic equation, what will be like that? U1 is nothing but phi 11 q1, phi 12 q2, phi 13 q3, right? For this response u2, what will have? Again we just multiply it, phi 21 q1, phi 22 q2, phi 23 q3, and simultaneously this. So what are they? They are the displacements. That means they are the responses. That means if you find out the mode shape and if you find out the modal coordinates, you can find out the displacement u in the modal coordinates. Whatever we have solved in that using the physical system, considering that a sine omega nt cos omega nt, b sine omega nt cos omega nt, and look for the responses like unt. Here in the modal coordinate system, it's quite easy. Mode shape multiplied by your modal coordinates. Mode shape multiplied by your modal coordinates. Got it, Bob? The point?
Yeah, it's clear.
Yeah. So by this way we can, like, for this system, if I now want to, this is an undamped system. Now if I want to elaborate this equation, so what will be the physical quantity for a undamped system? It's nothing but we know an cos omega nt plus bn sin omega nt. Okay. So total response, what will be the total response? Is summation of 1 to n cos omega nt, bn sin omega nt. Now you just differentiate it with respect to time, because we will use these equations in this modal coordinate system. What will be the initial condition? Again the initial condition u0 will be phi n into an, and u dot 0 will be phi n omega n into bn. Because put t is equals to 0 here at that equation for the initial condition u of 0, you will find that u of 0 is nothing but summation of phi n an, and u dot 0 will be become that. My point is not here, my point is next point. Like my physical response u is nothing but phi n into q. So if you impose the initial condition, we can find out the value of an and bn. So the an and bn comes as an comes as qn of 0 and bn comes as q dot of 0 and omega n. Recall, for SDOF system under free vibration case, we have find out an is equals to x naught and bn is equals to x dot naught by omega n. Similarly, here we have the modal responses in modal coordinates qn and wn. So what will be the value of qn? Qn we know phi nt mu by mn. Already we have derived on the previous slide that modal participation factor qn or the modal coordinates is nothing but phi nt mu, that means the initial condition, initial displacement divided by the component of the mass normalized matrix. So now your equation of motion, the solution is ready. U of t is nothing but summation 1 to n phi n q0 cos omega nt q dot 0 omega n cos sin omega nt. Now using this equation, you can easily solve the responses for this system. So if I want to know the displacement of ut, I can easily calculate. If I want to know the displacement of ut, I can easily calculate in terms of modal coordinates, mode shape and the generalized coordinates, mode shape and the generalized coordinates, because mass and stiffness property all will be provided. Clear? Okay. So it's very simple how we can calculate the use this concept and calculate the response. So first we need to formulate our characteristic equation, like k matrix minus omega square m is equals to 0. So we need to first calculate the determinant of this matrix. We need to find out the omega 1 square, omega 2 square, dot 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 omega n square. That means the corresponding eigen values of this eigen operation problem. Then what we need to do, we need to find out the mode shape matrix. We need to calculate the initial condition. Once we have the initial condition, we can find out the participation factor qn is nothing but phi nt mu or u0 precisely here, and mn the component of this. And once we have found out this, we can easily calculate the value of the total response and the response in modal coordinates. Okay. So if you want to solve one example, like here, determine the free vibration response of a structure due to the initial displacement this and this, right? Where the mode shapes are given phi 1 and phi 2. Now, how we can solve it? If you don't know the concept of modal participation and modal superposition and modal contribution factors, you cannot solve this. So now we can easily solve it. Like we have this u, we have phi 1, we have phi 2, right? What we need to do? It's a two-dop system. We will consider that m1 is equals to m2 is equals to m. So our mass matrix will be ready. And simultaneously we can solve the equation. So the mass matrix actually is given to the system. The mass matrix m is given like this: 2m 0 0 m. That means first degree of freedom have 2m mass, second degree of freedom have m mass, and the corresponding mode shapes are also given. Phi 1 is given as that, phi 2 is given as that. Initial condition u naught is given is this, and that means only initial displacement is given, no initial velocity are provided. So what we need to first provide? We need to first calculate the participation factor q1 0. Again the same formula, phi 1 t m u 0 divided by the first component of the mass normalized matrix, and q2. Once we have these two, we can easily found q1 of t is equals to, using this equation, q0 cos omega 1 t q dot 0 by omega n sin omega n t. So q1 t will become 1 cos omega n t. So this kind of questions may come. Okay. And for the rest of the system, say q2, you can also find out the solution in the similar way. That means you need to find out the Q2 value first, modal participation factor. Then you need to formulate this equation like Q2 is equals to Q20 cos omega 2t plus Q2 dot 0 omega nt sin omega nt. That means corresponding to the second degree of freedom system. If you have multiple degree of freedom system, say Qn of t, the general equation is nothing but it will look like Qn of 0 cos omega nt plus Qn dot of 0 by omega n sin omega nt. Now, for each of degree of freedom for each time point, you can calculate it. If you can code it, you can calculate it each time point within MATLAB and you can solve it. Great. Now, we have again that response of a damped free vibration case. So, damped till now, till now we have discussed about the undamped cases. Like here we haven't used any damping matrix, damping term yet, right? We solve the response. These are the response for undamped free vibration case. Look, here only you have Q and T we have used like an cos omega nt, bn sin omega nt. That means we have considered the natural frequency, no damping term, no decay term. E to the power minus xi omega nt we haven't used yet. Because we don't know the damping model, how we can use the damping model for the multi-degree of freedom system, all these things. So we will quickly spend some time on these damping models. So for the damping system, only one term will add, that Cn. So if I want to write a end of system in modal coordinates, what will look like? So it will look like m n, that means mass normalized matrix divided by Qn double dot plus Cn Qn dot plus Kn Qn is equals to 0. Free vibration case, so no external force will apply on this. So we can further simplify this equation like Qn double dot. Qn are the generalized coordinates or modal coordinates. Nothing but the degree of freedom, like x double dot y double dot in the physical system we have write down. Plus Cn, we know Cn, C is equals to twice xi omega n. So we can write it down twice zeta n omega n Qn dot plus K, we know, like we have multiplied both the side using this mn. So C by twice m omega n. So if I take out m here, so m will cancel out from here and C by m will be this. And Kn by omega n is equals to omega n square Qn is equals to 0. So like this. Now again we can write it this equation like what will be the physical response. Physical response, again we can write it down phi n into Qn. The physical response say Zn is equals to. So for the damped system, what is the generalized coordinate we need to know. So for the damping system, for the free vibration case, for first degree of freedom system, we know that x of t is nothing but e to the power zeta omega nt q naught 0 cos omega dt plus q naught 0 plus sine zeta n omega n q naught by omega dt sin omega dt. Already you have solved this equation, right? Where omega d is nothing but the damped natural frequency, omega n under root of 1 minus zeta square, right? So we have the Qn, that means the modal participation or modal coordinate for this damped system. Now we can easily express the displacement u of t is nothing but 1 to n phi n q n t. So phi n into multiplied by this whole expression. That means you will have the response u is nothing but the mode shape matrix phi multiplied by your coordinates, and coordinates for the damped system you know. So using this modal representation also we can solve the response of a free vibration case, damped or undamped both. So generally this modal expansion thing work when your zeta is, that means the damping is less than 20%. For the other cases this thing will not converge accurately. There will be error. Why there will be error, I will tell you when we will solve force vibration case in the modal coordinate systems. Now for the damping model, here look, I've already written C, only C. Why? How we can model this C? Can it be like a viscous damping model? Like in viscous damping model, what we know till now we have used that viscous damping model, right? In viscous damping model, we have assumed that my damping force is proportional to the velocity of this of the the system. That means FD is nothing but your C into X dot. But for the multi-top system, how we can deal with the damping property, we will see. So we have different kind of damping model. One is the Rayleigh damping model. So first we will go through that Rayleigh damping model, and again we have Caugh damping model for the multi-top system. So first we will let's see the Rayleigh damping model. What that Rayleigh damping model says. So here we have considered this two-top system again, swing mass system. So first degree of freedom have x1, second degree of freedom x2. Corresponding masses are m1 and m2. Initial conditions like the system is starting from the absolute rest. So we can easily formulate the equation of motion and write down the coupled equation. Say m1 m2 x1 x2 double dot plus c1 plus c2 minus c2 minus c2, and all these things already we have solved it. That means here this is my coupled equation, A matrix into X vector, again C matrix, again X vector, K matrix into X is equals to 0. So now in Rayleigh damping model, Rayleigh has considered the damping of the structure will depend on two things. That means mass dependent A0M and the stiffness dependence A1K. So he has proposed a model which actually correlate between your mass and stiffness. Okay. Now, so if we want to investigate the mass proportionality or mass dependency of this kind of model, so what we can see that mass, this portion will counteract for the mass dependency. So if I want to write it down, what will be that already we know that C is equals to A0M. That part actually catered with the mass proportionality portion. So if we want to use that modal information, that orthogonality of mode shape, if we multiplied phi n transpose phi n both side, what will happen? Transpose m phi n A0. So we will have normalized damping term Cn is equals to A naught Mn. Now why I am doing it, you will just find it out. So finally we will left with this term for the mass dependency Cn is equals to A naught Mn. Now if we further expand it, we know zeta n is equals to Cn by twice omega n Mn, right? So instead of Cn, if I write it down, zeta n is equals to A0 Mn divided by twice zeta n omega n. So I left with A0 is equals to twice zeta n omega n. Now recall when we discussed that critical damping portion CCR, what was the value of CCR? Twice zeta n omega n, right? So this is not CCR. Here he has considered this actually reflect the mass dependency. So A naught value we have found out, A naught is equals to twice zeta n omega n. Now we haven't completed it. Now if we want to establish the stiffness relationship, so stiffness, the second part, so the model was C is equals to A0M plus A1K. For the first part, A0 we have calculated. Now we need to look for this A1. What is the relation between A1 and zeta? So Cn, this part actually define the stiffness dependency. C1 is equals to A1K. Now again we know K matlab, that means omega is equals to under root of K by M. So we can further simplify it like that. Cn is equals to A1 omega n square Mn, right? So ultimately Cn we can write like in the term of zeta. We know that zeta is nothing but C by C CR. So precisely in that equation, instead of C, if you use Cn, A1 omega n square Mn divided by CCR, we know the value of CCR twice omega n Mn. So we left with zeta k is equals to A1 omega k by 2, which actually leads to A1 is equals to twice zeta k omega k. Now, we have the value of A1 is equals to twice zeta k by omega k. We have the value A0 is equals to twice zeta n omega n, twice zeta n omega n. So you can see that A naught is proportional to your omega n and A1 is proportional to your 1 by omega n. That means that two part, the mass dependency is directly proportional to the natural frequency, but it is inversely proportional to the natural frequency. Now, if we want to construct this model with respect to these frequencies and the coefficients, the model will look like this. So C we have is equals to this. So we can express this formula like this: zeta n will be equals to, that means zeta n is nothing but your C by C CR. So you can do the math here over here, and finally your zeta n, the final equation of zeta n will become A naught by very simple equation twice omega n plus A1 A1 omega n by 2, I think. Yeah. So if I simplify again, zeta n will look like half A naught by omega n plus A1 omega n. So this is the final formula for damping ratio corresponding to each node and each natural frequency. Here you can see zeta n is equals to A naught by twice omega n plus A1 omega n by 2. So for example, we have 2 degrees of freedom system. Okay. The first natural frequency omega n is 2. Say second natural frequency omega n is equals to 4 rad per second, rad per second. Now calculate what will be the damping ratio zeta 1 as per the Rayleigh damping model. We can easily calculate it. Now the point is here, like we have seen, if we have two natural frequencies corresponding to two modes, how we can find out the zeta 1? Zeta 1 will nothing but A0 by twice omega 1, A1 omega 1 by 2, and zeta 2 will be A 0 by 2 omega 2. That means just change the indexing for this. So we have seen that the mass dependency property will lead like this, follow like this, and the stiffness dependency property will follow like this, like, because we have already established. So ultimately the Rayleigh model will look like this. The zeta value of the Rayleigh model will look like this. Zeta n is nothing but, it's a very simple formula, A naught by twice omega n plus A1 omega n by 2. You can easily calculate the damping ratios at each node corresponding to each natural frequencies. Like we have Caugh model. Like if we have here, we can see like we have two unknowns, so we can only solve two for the two modes only. So if we want to solve for more modes, we go for the Caugh model. So I will discuss the damping model in details on the next class. So today just quickly go through solve the examples, and then we'll wrap up the session, because that discussion of the damping model and elaborate the things including the physical effects, it will take time and we don't have time today. So let's quickly solve the questions related to relay damping. So here, like we have again a MDOF system where mass matrix is given, damping matrix is given. Look, two frequencies are given, omega 1 and omega 2. Calculate the modal damping ratios for first and second mode. That means you need to find out zeta 1 and zeta 2 as per relay damping. So how we can calculate it? So we need to calculate like we already have the expression zeta 1 and zeta 2. So the zeta 1 value, Here you can see the expressions for zeta 1 and zeta 2. A naught by twice omega 1, a1 omega 1 by 2, and a naught by twice omega 2, a1 omega 2 by 2. Just you need to replace this and solve for the answers. These two. Okay. Just cross check the answers. Okay. Now again here we have again that Rayleigh damping term zeta n. For this, like the problem says, the Rayleigh damping coefficient a0 value, a0 is given 1.1, a1 is given as 1.8 into 10 to the power minus 3, and omega 1 is given as 45 rad per second. You need to find out the zeta 1. Zeta 1 will be a naught by twice omega 1 plus a1 omega 1 by 2. The value of a1 is given 1.1 divided by twice into 45 plus a1, the value of a1 is given 1.8 into 10 to the power minus 3 into 45 divided by 2, and that comes as 0.0527. That means almost 5%. Again, we have similar kind of examples, like the natural frequency of two modes of a two-story building are given as 14 rad and 36 rad. So omega 1 is given as 14 rad per second, omega 2 is given as 36 rad per second. Calculate the value of Rayleigh damping coefficient such that the damping ratio is 5% for the first and second modes. The damping ratio, okay. Rayleigh's coefficients, that means you need to find out the A0 and A1, where zeta 1 and zeta 2 is given as 0.05. Simple, straightforward. You need to use this equation. Zeta n is equals to A0 by twice omega n plus a1 omega n by 2. So first you need to find out the equation for zeta 1, you need to find out equation for zeta 2. Now once you have these two equations, you need to look for a0 and you need to look for a2, because a1, you have two unknowns, you have two equations, you can easily solve it. So the a1 value by a0 value I have calculated is 1.008. Please recalculate these values. 002. And we say you just need to formulate two equations. Zeta 1 and zeta 2 values are given. 0.05 is equals to a naught by twice into omega 1 value is given 14. So 14 plus a1 into 14 by 2. For the second mode, 0.05. A0 divided by twice into 36. For the second mode, 36 plus a1 into 36 by 2. You just need to these two equations 1 and 2. If you solve it, you will find out a1 and a2. Clear? Do you have any kind of questions?
No, it's fine.
Yeah. Then okay, we will continue on the next class. Like let's quickly discuss this few MCQs. Like the modal stiffness matrix of a MDF system. What is that? It's always a diagonal matrix, right? Modal stiffness, modal, not normal stiffness. Modal stiffness. K normalize with so obviously it will be diagonal. Great. Now a structure is assumed as classically damped when the damping matrix is symmetric matrix. Okay, for the Rayleigh damping, when we can use the Rayleigh damping model, very important thing, just quickly I will tell you. This Rayleigh damping model we can only use when C M inverse K is equals to K inverse C. This the damping model will satisfy, or the system will satisfy this property. C M inverse K is equals to K inverse C. That means all the roots will be positive, correct? So to satisfy this property, it needs to satisfy the orthogonal properties. That's why the answer will be orthogonal. So symmetric matrix, actually symmetric matrix, right? Only when the symmetric matrix will be there, then only this that property will be satisfied. Symmetric matrix, right? Now, for a 5 degree of freedom system, if the natural frequencies of the first and fifth mode are omega 1 and omega 5 respectively, then what will happen? Omega 1, omega 2, omega 3. Obviously, omega 1 is less than omega 2, less than omega 3, less than omega 4. So, obviously, B will be the correct answer, right? Okay. So, okay, now we will meet again on the last class. If you have any kind of questions, you can ask me, or we can close the session for today. And Bob, how your work's going on?
Ah, very, very, very tedious. Plenty things to do at the same time, but
Uh,
it's fine.
yeah. And you are doing your PhD, right?
Yes.
Yeah. So how is your research work going on? Like you are
Uh,
working on which domain?
um, construction management.
Okay. Okay. So there, what you are doing, optimization things you are doing, or you are catering that part uncertainty, how we can counteract
Exactly.
uncertainty.
It's more of uncertainty. It's particularly about risk in construction.
Yeah, obviously, where there is risk, there is uncertainty. You can quantify the uncertainties related to that risk. It will be huge work, right? If you have a model,
Absolutely.
yeah, if you have some model which can quantify the uncertainty of this risk management strategy, then your work will be done, and you can use that probability and random theory. Like we have to quantify uncertainty, we have different kind of statistical tools, so you can use that
Yes.
model. Like
Yeah. Yeah.
yeah, it's a great work. Like
We-
how to risk manage,
Yeah.
how to optimize the uncertainties related to that risk management part. So I will suggest like if you go for the uncertainty quantification and reliability analysis of this risk management strategy on you are going on. So I think very few work has done on that field, and
and
considering
and I,
complete randomness of the model, considering.
and I want to tailor it to fit the African context, particularly Ghana.
Okay, okay. So you have data also. Then you can easily model it, right? You have the data, all the data, right?
No, no, I've not collected the data yet. I've not been given the ethical clearance to collect data. So
No. Like
once I,
previously use some strategy, previously use some data. No needed. You can generate samples also. Like I'm working on this sample, the predicted portion will be that, and after prediction, there may be this kind of uncertainty related to this problem, like that kind of problem from the sense.
we'll have more discussions with time so that
Yeah,
we know what to do.
yeah. Obviously.
Good, good, good.
So okay then. Thank you.
Thank you very much. So we'll talk.